In this video, we use the open source free software Maxima to derive the commutation relations we talked about near the end of the main video. So first we want to show that the commutator of position and momentum is equal to IH bar. So the operator x hat, that is the position operator, is just multiplication by x. The momentum operator p hat is minus IH bar times the slope in x. And so we want to show that x times p hat operating on the wave function psi minus p hat operating on x times the wave function psi is equal to IH bar times the wave function psi. So we open up Maxima, and there's a link below to a video talking about where to get Maxima and how to basic operation of it. In the first line, in blue is the input and black are the outputs from Maxima. We say depends psi x. Psi depends on x. It's a function of x. And then we define the momentum operator. P operating on some wave function u is defined to be minus I times h over 2 pi, which is h bar, times the slope of u in x, or the differential of u over the differential of x, or the derivative of u with respect to x. Anyway, this notation we use in Maxima is diff u comma x. So then Maxima echoes out that definition, and now we simply say RATSimp means rational simplification. Just simplify the resulting expression as much as it can. X times p operating on the wave function psi minus p operating on x times the wave function psi, and the result that comes out is I h over 2 pi, that's I h bar, times the wave function psi. So we've just demonstrated that commutation relation. Now we want to demonstrate the commutation relations for angular momentum. So the operators for the x, y, and z components of orbital angular momentum, as we showed in the main video, are minus IH bar, y times the slope in z minus z times the slope in y, and then kind of permutations of that formula. And we want to show that the commutator of L hat x and L hat y is equal to IH bar L hat z. So we open up Maxima and we say depends psi on the three values x, y, and z. Okay, so it's psi is a function of position in space. We define our three angular momentum operators. Lx operating on a wave function u is defined to be minus I h over 2 pi, that's h bar, times the quantity y times the slope of u and z minus z times the slope of u and y. And then similarly for L sub y and L sub z. So those are our three operators. So now we form the commutator of Lx and Ly. I just give it the label CLXLY. And again, RATSimp, rational simplification, just simplify the result. I get Lx operating on Ly operating on the wave function, minus Ly operating on Lx operating on the wave function. And the result I get, well, it looks like minus h squared over 4 pi squared. That's minus h over 2 pi quantity squared. That's minus h bar squared. And I get y times the slope in x minus x times the slope in y. And if you look up at the LZ hat expression, that's the LZ hat expression just with an extra factor of I h bar. So we've shown that commutation relation. And then it's simple to just change the x, y's, and z's to get the other two commutation relations.